Hello everyone, I welcome you to another video lesson. In this video lesson, we'll focus on models from queuing theory. We come across queues in every walk of life. Whenever we take a ticket at the counter or we look for refreshments at a cinema, there are always queues around. We look at how queues can be modeled and analyzed mathematically using various models. We look at one of those models in today's video lesson. We'll start with a simple problem, and through that we'll understand the various notations and the concepts involved. The question reads as follows: customers arrive at a box office window being manned by a single server according to a Poisson input process with an average of 20 customers an hour. The time required to serve a customer has an exponential distribution with an average of 90 seconds, and we are expected to find the average waiting time of a customer in the queue. Now, when we learn models like these, we'll understand the notations involved with the analysis of these models. For that, we'll look at the various notations, the various symbols involved while describing a model. Most models can be classified into one of these models that we'll learn across this course of video lessons. First model is termed as MM1, infinity, and FCFS. The first M denotes the arrival rate, which follow a Poisson process. The second M denotes the service rate, which follows an exponential distribution. The one denotes the number of servers that are available for serving the customers. The infinity will denote the capacity of the queue, and the FCFS will denote the discipline, which thinks that the customers who arrive at the queue are served on a first come first served basis. And then we have these notations which will help us identify various answers connected to the queuing model. The first of them is known as LS. LS will denote the average number of people expected to be present in the system at any point of time. LQ will denote the average number of people expected to be present in the queue. The queue and the system are different. The system is the queue plus the counter where the service is offered. So we use different notations for both. The system is denoted by LS and the queue is denoted by LQ. WS is the average waiting time for a person in the system, and WQ is the average waiting time for a person in the queue. P naught will denote the probability that there are zero customers in the system, the queue, as in the queue is completely free, anybody can walk in and get their service done. Pn will denote the probability that there are n customers in the queue, and P of n greater than n1 will denote the probability that there are at least n1 customers in the queue, and P of w greater than t will denote the probability that the waiting time for a customer is more than t units. And we have the following formula for this first model, which is an MM1 infinity FCFS. The arrival rate is denoted by lambda, the service rate is denoted by mu. Denote that. Please remember that both of these are in terms of rates. The arrival rate is always paired up with a per hour or a per minute or a per second kind of a unit. The traffic intensity denotes how busy the queue is. That's the ratio of lambda to mu. Ls is given by rho by 1 minus rho. Lq is denoted by Ls by lambda minus mu. Ws is Ls by lambda and Wq is Lq by lambda. P naught is 1 minus rho. Pn is rho to the power of n plus 1 for this model. Further, the probability that a customer waits for more than t units in the system is directly defined by the function e to the power of mu minus lambda t, and probability that a customer waits for more than t units in the queue is defined by e to the power of minus of mu minus lambda t multiplied by the traffic intensity rho. Now, we'll get back to the problem that we started at the beginning of the video lesson, and let's try and solve this using the formula we learned. From the question, it is obvious that the arrivals happen following the Poisson process at the rate of 20 customers per hour, so lambda is at 20. The service also follows exponential distribution. This is part of the problem. You can identify that from these two parts of the question. The arrival is a Poisson input process. The service follows an exponential distribution. And there is only one server because the question mentions that there is one box office window. Further, we are told that it takes 90 seconds to serve one customer, and this will give us the service rate. But it is essential that we express both the arrival and the service in terms of similar units of time. So the arrival says that there are 20 customers per hour. So we also try and express the service in terms of the time unit, which is an hour. So for that, we do the small calculation. It takes 90 seconds for one customer, which means it takes 180 seconds for two customers, and 180 seconds convert to 3 minutes. So two customers can be served in 3 minutes. Multiplying both sides by 20, we see that 40 customers can be served in 60 minutes, and 60 minutes convert to an hour. So we conclude that 40 customers can be served in 1 hour. So the service rate for the queue is 40 customers per hour, and the arrival rate for the queue is 20 customers per hour. So both arrival and service are expressed using the same time unit, which is an hour, and that will help us make our calculation even more simpler. So now that we know what lambda is, and now that we have also determined the value of mu, we can go ahead and solve the problem. So lambda is at 20, mu is at 40, which means the traffic intensity rho is the ratio of lambda to mu, which is at 20 to 40, which is at half. So Ls is rho minus rho divided by 1 minus rho, that's 1. LQ is Ls minus lambda by mu, that's half. WQ is LQ by lambda, which is half of 20, and the time unit is in terms of hours. So it is 1 by 40 of an hour, which and which we can convert them into minutes. It simplifies down to 6 by 4 minutes or 1.5 minutes. So the average waiting time for a customer in the queue is 1.5 minutes. That helps us solve the problem. This is in the queue. WQ is what we are expected to find out, and we have found out just that. So we'll repeat the same process for other problems for the same time. Question 2 reads like this. Customers arrive at a self-service store with one cashier at the rate of 9 customers for every 2 minutes, following a Poisson process. So the first M in the description of the model is identified here because the arrival follows a Poisson process, and the arrival rate is 9 customers for every 5 minutes. The cashier serves 10 customers in 5 minutes following an exponential service time. So the second M in the model is also identified, and there's only one server in the model because there's only one cashier available, and we are supposed to find the average number of customers queuing for service, the chance that there are more than 10 customers in the system, and the probability that a customer has to queue for more than 2 minutes. We'll find all that by first looking at the data. The data says arrival follows a Poisson process with 9 customers for every 5 minutes. So in 5 minutes, we have 9 customers multiplying both sides by 12. 60 minutes converted to 9 times 12, which is 108 customers. So we have 108 customers every hour. So lambda is in terms of 108 customers in an hour. Now we look at the service rate. The service rate shows that 12 customers are served, 10 customers are served in 5 minutes. 10 customers in 5 minutes, multiplying both sides by 12, we see that 120 customers are served in 60 minutes. The 120 customers are served in an hour. So mu is 120. So lambda is in terms of hours. Mu is also in terms of hours. We have done the conversion into the same convenient unit of time. So we can move forward and solve the problem. So we have the number of cashiers, the number of servers. The question says that it is exactly one server, which is part of the problem's description. So, so the number of servers here is just one, and there is no information about the capacity of the queue. And as long as there is no information, we understand it as an infinite capacity. And the discipline here is again first come, first served because there's nothing else mentioned to understand otherwise. The traffic intensity, which is the ratio of lambda to mu, is 108 to 120, so it's 9 by 10. So we know what rho is. The average number of customers queuing for service, LQ, we know LQ is expressed in terms of LS. We first express LS in terms of rho divided by 1 minus rho will give us uh, 9. And when we subtract lambda by mu from that, we have 9 minus 9 by 10, which is 81 by 10. So 81 by 10 is the average number of customers who are waiting in the queue for service. This approximately 8.1. And then we have the probability that there are more than 10 customers in the queue. That's rho to the power of 11. We know what rho is. That gives us the answer of 0.3138. And the probability that a customer waits for more than 2 minutes in the queue. And we know that this is expressed using rho and the exponential distribution. So it is rho times e to the power of minus of 120 minus 108. So that's 0.9 times e to the power of minus 4. That comes to 0.6. So the probability that a given customer waits for more than 2 minutes in the queue is 0.6. Let's move to the next problem. It's a pretty long question, so I'll read through it one by line by line. An airline has one reservation clerk. That's the first clue for us. There's only one server available for serving any customer available. So the reservation clerk is just one. He handles information about flight schedules and makes reservations. All calls to the airlines are answered by an operator again. If a caller requests for information on reservation, the operator transfers the call to the reservation clerk. There's only one reservation clerk. The clerk is busy. The operator asks the caller to wait. This is a second clue, which says that anybody who arrives at the queue when another service is already going on must wait. When the clerk becomes free, the operator transfers him to the call of the person who has been waiting the longest. So this follows the classic FCFS discipline model. The next paragraph tells us that the arrivals and services follow Poisson and exponential distributions. The calls arrive at a rate of 10 calls per hour, and the reservation clerk can service a call in 4 minutes on the average. And we are asked to find the average number of calls waiting to be connected to the server, the average time a caller must wait, the average time for a caller to complete a call. Now, the customer completes a call, and this time is inclusive of the waiting time plus the service time. We'll make use of that in the problem. So obviously, we made our first observations about the problem. There's only one reservation clerk, so that's one server. And if the clerk is busy, the caller will wait. So that's an FCFS discipline. And the capacity is infinite because we don't have information, otherwise limiting the capacity of the system. The calls arrive at the rate of 10 per hour, so lambda is at 10. That's in terms of hours. The time taken for service, it says one call can be completed within 4 minutes. So we'll convert that into hours by multiplying both sides by 15. 60 minutes for 15 calls. So we have mu or the service rate at 15 calls per hour. So once we know that what lambda and mu are, we know the traffic intensity as a ratio of lambda to mu, which is a 2 by 3. Now with that, we can proceed forward and find the answers that are required. The average number of calls waiting to be connected. Waiting to be connected as in the service hasn't yet begun. So this caller is still in the queue. So waiting to be connected will mean that we find out LQ. The average number of calls waiting to be connected, we'll look at LQ. LQ is represented in terms of LS and lambda by mu. So we know what LS is, that's rho divided by 1 minus rho. So we know what rho is. Rho is a 2 by 3. That simplifies down to 2 as the value of LS. And LQ is LS minus rho. That's 2 minus 2 by 3. It simplifies down to 1.33. So the average number of calls which are yet to be connected is at 1.33. The average time for a caller to wait before his call gets placed is at WQ again because he's waiting. So WQ, we know that WQ is the ratio of LQ to lambda. That's 4 by 3 upon 10 of an hour. That's 4 by 30 of an hour. That's 4 by 30 of 60 minutes. That's come down to 8 minutes. For the last answer, the average time for a caller to complete the call, like I said before, completing the call includes the time he waits at the queue and the time he takes for his service to be completed. So that's WS because that's the number of time he spends at the system, number of minutes he spends at the system. So that's LS upon lambda. We know LS, we already determined LS in the previous screen to be 2. 2 by lambda is 2 by 20. That's one-fifth of an hour or one-fifth of 60 minutes. That simplifies down to 12 minutes. That answers all three questions that were asked of us. The next problem, we'll once again read through this long question. A repair shop is surrounded by a single mechanic. That's our first clue. When we say there is a single mechanic, the number of servers that are a part of the system is restricted to just one server, and he has an average of 4 customers an hour. So there is an average of 4 customers visiting the shop. That gives us the clue of the arrival rate. The mechanic inspects them for defects and often fixes them right away after the diagnosis. And he takes 6 minutes to complete the diagnosis and completing the repair job. And if the arrivals follow Poisson distribution, this classifies the model of the queue. That is the first M of the model. It follows a Poisson distribution, and the service takes an exponential distribution. So the second M in the description of the model is also clearly identified. We're supposed to determine three answers: the proportion of the time the shop is empty, the average number of customers who are in the shop, and the average time spent by a customer in the shop. All right. So let's look at the data given. A single mechanic, one server. The capacity is infinite because there's no information hinting at a restriction to the capacity. The discipline is first come, first served because once again, there's no information about the uh, other kind of disciplines which are possible. The other kinds of disciplines that are possible are first in, last out, or last in, first out, or service in random order. None of that is specifically mentioned in the problem. So we can take for granted that it is a first come, first served model. So the arrival rate is 4 customers an hour. So that clears the value of lambda. Lambda is 4 per hour. The service time it takes is 6 minutes for one customer. So multiplying both sides by 10, we say that 10 customers can be served in 60 minutes or 10 customers can be served in an hour. So mu is at 10, lambda is at 4. The traffic intensity is lambda by mu, which is the ratio of 4 to 10 at 2 by 5. So the proportion of the time the server is empty. The server is empty if there is no one present in the system. That that is denoted by the notation P naught. The P naught is saying that there are 0 customers in the system. So P naught is 1 minus rho because rho is the proportion that it is busy. 1 minus rho is the proportion that it is not busy. So 1 minus rho is 1 minus 2 by 5. That's 3 by 5. In terms of percentage, that's 60% of the time that the shop is empty. The average number of customers in the shop. The customers in the shop is the customers in the system. That's LS. LS we know is the ratio of rho to 1 minus rho. So 2 by 5 to the ratio of 3 by 5. That's 2/3. So LS is at 2 by 3. That's the first constant we are supposed to determine. And next we are supposed to determine the average time spent by a customer waiting in the shop. Waiting in the shop will include the time spent in the queue as well as the time taken to complete its service. So that's WS. WS is the ratio of LS to lambda. That's 2/3 upon 4. That's 2 by 12 of an hour, or 2 by 12 of 60 minutes. That's 10 minutes. So the average time spent by a customer in the shop is exactly 10 minutes. Okay, for the last problem of the day, we'll look at this question. In a cafeteria managed by a single server, orders arrive at the rate of 10 per hour, and the server takes up to 4 minutes to complete one order. They're expected to find this time spent waiting for the turn to place an order if arrivals and service follow Poisson distribution and exponential distribution. We identify that there's only one server in the system. That's evident from the first line of the problem. And the arrivals and service follow Poisson and exponential distribution, which means the two M's in the model MM1 are identified. So it's a cafeteria. So we'll assume that the discipline is FCFS. And the arrival is at 10 per hour. The time taken for one order is 4 minutes. 4 times 15 will include 1 times 15 customers. So 15 customers are served in 60 minutes. So 15 customers are served in an hour. So lambda is at 10, mu is at 15, and that will help us find all the answers that we need. And we are expected to find only one part of the problem: time spent waiting to place an order. So since they are waiting in the queue, we're supposed to find WQ. WQ is the ratio of LQ to lambda. All right, now we know that lambda is at 10, mu is at 15. We have the traffic intensity as 2 by 3. And WQ depends on LQ and lambda. LQ in turn depends on LS. We find LS. LS is 2 by 3 by 1 by 3. That comes down to 2. And LQ would be 4 by 3. And lambda Q is directly identified as 4 by 3 upon lambda. That's 4 by 30 of an hour, or 4 by 30 of 60 minutes. That comes down to 8 minutes. The average time a customer has to spend waiting for his turn to place the order is at 8 minutes. So this video lesson must have given you a comprehensive review of various problems that can be solved using the first model of queuing theory. We'll look at other similar models in the subsequent lessons. Thank you for watching.